research from scratch. And I said, no, go boil them. Just buy them at Walmart. We had this conversation because I was
Make sure you have a calculator today.
I can verify. I can verify if that was in the conversation. Sorry. Yeah, you guys wouldn't eat ketchup and you thought it was weird.
We're going to need a calculator the rest of the year, so just make sure you have it available. All right, so last week we were kind of introducing parametrics and vectors. We're going to take a look at vectors a little bit more today, just with some kind of free response type questions, different calculus operations we can do to these vectors. So kind of as a review here from not Algebra 1, back in Calculus 1 or last year, we talked about integrating velocity, aka working backwards from velocity. And when you do that, notice how they're representing the velocity vector as the x derivative comma the y derivative. We talked about that kind of last week. Remember, velocity is the first derivative of position, so you're just going to write your first derivatives kind of in a coordinate notation. You can use parentheses or those chevrons, kind of like the arrows. So if you take the derivative of position, you get velocity, but if you work backwards from velocity, that should tell you something about your position. But it's not your position exactly, it's your displacement. Okay, kind of how much you've traveled on this time interval, whatever it is. So this isn't your position exactly, it's your change in position. Specifically your change in x coordinate and then your change in y coordinate. Total distance, on the other hand, is when you integrate velocity with absolute value, because we don't really care about negative velocity, meaning traveling to the left. We just care about the numbered value itself. That's why we put the absolute value bars. And we talked about this distance traveled last week. Remember how that came from the Pythagorean theorem? Does that look familiar? Okay, so when it's asking for a particular position, perhaps, we're just going to integrate the individual derivatives. But if it's asking for the total distance traveled, aka that arc length around a parametric curve, we're going to utilize the square root of the derivative squared summed together. Okay, so both of them are some type of an integral. We just have to be careful on which one we're actually using. So today's just going to be practice with these and getting used to different free response type questions for these vector problems. All right, so the first one, an object moving along the curve has some position x of t, y of t. So this is basically telling you that you're using some type of parametric set where you have one equation that tells you the x coordinate and one equation that tells you the y coordinate. And they give you the x derivative and the y derivative, or the x rate and the y rate. And at time 2, the object has this position, an x coordinate of 1 and a y coordinate of 4. Find the acceleration vector for the object at time 2. So vector, we're going to need either chevrons or parentheses, some type of x acceleration and some type of y acceleration. Where do you want to go from there? Think about the order of your functions in terms of this particle movement. Is there some way we can figure out the x acceleration? There we go. So this is like your x velocity, and this is your y velocity. Those are the derivatives. So we got to take the derivatives of each of these individually, and we'll essentially plug in 2. Do you notice how this is a calculator active question? And it says calculator at the top. Do we remember how to find the derivative of a function at a point? on the calculator. We could find the derivatives by hand. Okay, we can use the product rule, chain rule, quotient rule, whatever applies. But since we have a calculator, maybe that will be a little quicker. Do we remember where to go? Math. Option 8, right? All right, first box is always an X. I know it's T's on your paper, but we'll do X. And then maybe we want to take the derivative of the X velocity. So we'll do X sine of X, make sure you're in radian mode. And we specifically want to evaluate that at 2. So it looks like our X acceleration is 0.077. All right. Let's do the same thing, but for the y velocity. So math 8x, and we're going to type in cosine of x squared. Evaluate at 2, 3.027. Alright, so if you have a calculator, and you're trying to find the derivative specifically at a point, you can go ahead and plug it in on here. If they were just asking you for the acceleration vector, okay, if they didn't say at time 2, we would actually have to figure out the derivatives by hand and put in the derivative of velocity for x here and the derivative of the y velocity here. Do you see the difference between the two questions? If it didn't say at time 2, we would specifically just write in the derivatives. But since it was time 2, we can use our calculator. Okay? Let's try the next one. Write the equation of a tangent line to the curve at the point 2. What do we know? What do we need to know to write the equation of a tangent line? A point and a slope. All right. So at time 2, do we know what the point is? 1, 4. They gave it that to us at the top. All right. And then we need the slope of the curve, that parametric curve at time 2. How do you think we can figure out the slope of the curve? We have the slope of the x coordinate and we have the slope of the y coordinate. How can we combine those together for the slope of the curve?
How would you use that type?
This one up here?
Yeah.
That's for total distance. We'll get there eventually. It's just asking for the slope of the curve. So if we know the individual derivatives, we can just do the y derivative over the x derivative. So that would be cosine of t squared over t sine of t. And we got to plug in 2 for those t's. See, I got negative 0.359. Alright, so our equation, let's see, y minus 4 equals negative 0.359, x minus 1. We're doing okay so far? Okay. What about the speed of the particle at time 2? let's see, we know the x speed and we know the y speed. How can we figure out the overall speed?
Is this the
That's the Pythagorean theorem, right. So we got to figure out the x speed or velocity at 2. We got to figure out the y speed or velocity at 2. And then we'll use the Pythagorean theorem to figure out the overall velocity or speed. So the x speed at 2, 1.8186, and then the y speed at 2, negative 0.6536. All right, so the velocity or the speed would be Pythagorean theorem. We would need the square root of those values squared. I just got a bunch of calculator work from there. $1.932. We don't really have, they don't give us units, do they? Doesn't look like it. Okay, so we'll just leave it like that, 1.932. All right. We still have some more questions about this particle on the back, so we might have to flip our page to reference if we have to. Let's see the next one. Find the displacement of the object from 2 to 7. How do you want to try that? How far it is from where it started. Specifically at time 2, because that's our lower bound. Of the derivatives. Okay, so let's go ahead and figure out maybe the x displacement first. So we would have to integrate the derivative of x, or that velocity of the x coordinate. And what was that? T sine of t. Again, we have our calculator, so we can go ahead and type that in. And then we'll do the same thing for the y velocity. Cosine of t squared. Can we get those numbers from the calculator? Is it working out? Okay. I know this isn't part of the question, but what if there was like a second part or part B or something that asked you about the position of the particle at time 7? How can we figure that out? Not quite. Is that your go-to? Use the Pythagorean theorem?
Yes, I was just thinking because we know what the starting position is.
Okay, well at time,
Changing the y.
there we go. Okay, you're on the right track. If we know the position at time 2, And this is how much the x-coordinate changes. Okay, this is your displacement. This is how much it changes up to time 7. Can we figure out what the new x-coordinate would be?
I think it'd be 1 plus the displacement.
1 plus the displacement, right? So that would end up being negative 5.362. You start at 1, and you have a negative change of 6.362. So your ending x position at time 7 would be the negative 5.362. We could do the same thing for the y-coordinate. If you start with a y position of 4, and you change 0.097 units, then you end at 4.097, bless you, at time 7. So we just got to take how much we start with, in this case plus the change, and we'll get where we end at time 7. All right, let's try E. Find the distance traveled, basically total distance traveled by the object from 2 to 7. Eric, what do you want to do?
I guess Pythagorean.
This one's a Pythagorean theorem. Okay, so we're going to go from 2 to 7, and we're going to integrate the total velocity, which would be that result from the Pythagorean theorem. And we need the velocity, I guess, component vectors. So we would need the x velocity squared plus the y velocity squared. We get 13.229. Does that work? Should I take, yeah.
So from here, we just basically from its original starting point
Mm-hmm.
and its final starting point at 7, we've just drawn a straight line between the two, right? And then we found the distance of that line, correct? Is that essentially what happened?
This, okay, so if you, let's see, 1, 4, we'll say is here. And then this we know is where we are at time 7. So negative 5, a little bit more than 4. The particle might not be traveling in a straight line, because it might be like some type of curve. So by integrating the absolute value, or by integrating the total velocity, you're getting the length of that curve, the length of the arc. So that,
Okay.
so this is how much it actually traveled, but those are the displacements, like just this change and that change.
Okay.
Okay?
So that's what I was thinking, but for some reason I'm thinking that the equation we just solved for is just giving us the straight line, not the curves.
This was giving us the straight lines in a sense of x change and y change.
Okay.
But this is giving us the length of the curve, which is not necessarily straight.
So if we took the Pythagorean theorem of our x change and y change, it would give us the total change, correct?
Mm-hmm.
Okay. Just the displacement.
Yep. All right, let's check out F. Find the position of the object at time 1. Maybe we can reference part D to help us with that, because we were able to figure out the position at time 7, even though that really wasn't part of the question, but this one is very similarly stated. We're just looking at time 1 here. So let's see, at time 2, we know the position is 1, comma 4. What do we have to figure out in order to get the position at time 1?
It's displacement.
its displacement, how much it moved or how much it changed. So let's go ahead and use the integral from 1 to 2. Okay, the time that they're asking us about, and then the time that we know a coordinate from. So we'll have to integrate both component velocity equations. We'll do the x velocity and the y velocity. Let's see, can we get 1.44? And the other one is negative 0.443. Do those check out? Okay. So let's think about this. This is your change in x value, and this is your change in y value. How can we figure out this position at time 1? This time we have to subtract the displacement, because notice how they're giving us a point at time 2, but they're asking us about a point at time 1. Do you see how that's kind of in the past of what we know? So if this is how much we change from time 1 to 2, and we know the ending point, we'd have to subtract that change to get the beginning point, or that time 1 that we're looking for. So you kind of got to be careful, because when we did part D, we had to add the displacement, but that's because time 7 is in the future of that time 2 that we know. This time it's in the past. So we got to take 1 minus 1.4. So that'd be negative 0.44. And then 4 minus negative 0.443. So that would actually change to a plus. Okay, so a little different. It depends if the time interval is ahead of that point that they give you or behind that point that they give you, whether you add or subtract the displacements. We doing okay? We're going to try another free response type question. All right. An object moving along the xy plane has that position. Notice again how it's parametric. They give you an x equation and a y equation. The x derivative, or the x velocity, is given. The derivative of the y equation is not given. At time 2, we know a position. Find the x-coordinate of the position of the object at time 4. What do you want to do? We know the x position at time 2, that's 3. How can we figure out the x position at time 4? Displacement. All right, so we're going to go from 2 to 4, and just the x coordinate, so we got to integrate the x derivative, or that x velocity. So 2 sine of t squared. I got negative 0.115. So how are we going to combine that number with the x-coordinate of 3 from that beginning point in time 2 we know? Do we add it or subtract it? That's the big question. We're going to add it, right? Because time 4 is in the future of that time 2 that we know. So 3 plus negative 0.115, 2.885. All right. Let's try part B. At time 2, the value of the y derivative is negative 6. Write an equation for the line tangent to the curve at the point x2, y2. All right, so tangent line, we need a point and a slope. Do we know the point at time 2? That was 3, 5, good. And we need the slope of the curve. So it's not just the y derivative, it's not just the x derivative. We got to combine those to get the dy over dx kind of overall derivative of the curve. So at time 2, the y derivative is negative 6. And the x derivative, they gave us another page. Let's see, 2 sine of t squared. So let's go ahead and plug in 2 for that t to get our overall derivative. .964. Okay, so equation would be y minus 5 equals 3.964 times x minus 3. All right, part C. Find the magnitude of the velocity vector at time 2. That's a lot of wording that just represents one simple word. Magnitude of the velocity vector. What do you think that also means? AKA, what's kind of another word for velocity? Speed, right? This is basically just your speed. Because remember, velocity is speed and direction. When it's talking about magnitude, it's just that speed part. So find the speed of the particle at time 2. Eric, what do you want to do? Pythagorean theorem. All right, so we need the square root of the derivatives. Let's see, the x derivative was 2 sine of t squared. Do we know the y derivative at time 2? That's negative 6, right, from part B? All right, so we're going to plug in 2 for that time of t, and we should get our overall speed at that point. We get 6.188. Okay. We doing okay? So far? So far? Okay. All right, let's check out the last one. For time greater than or equal to 3, the line tangent to the curve has a slope of 2t minus 1. Find the acceleration vector, there's that word vector, so we're going to need those chevrons or parentheses, of the object at time 4. Oh boy. Okay, so we know the x derivative that was given to us at the very beginning, but they only gave us the y derivative at time 2. They said that was -6. Notice how for this time we're looking at 3 or more, so we cannot use that -6 as the y derivative. But they do tell us something about the overall slope. It's 2t minus 1. Let's see, we know dx over dt is 2 sine of t squared. How do you think we can figure out the y derivative? Because if it's asking us for the acceleration vector, we need the x derivative and the y derivative separately. That way we can evaluate those. What do you think we could do? Let's see, the line tangent to the curve at this point has a slope of that. This is your overall derivative. So we could label this as dy over dx. What do you want to do?
Can you just like put 2 sine t squared over, or dy over 2 sine t squared, and then set that equal to 2t minus 1?
There we go. We don't know the y derivative, so we'll just use dy to represent that. We do know the x derivative, and they also give us the overall derivative, which was 2t minus 1. So if we multiply over that denominator, we'll get 4t sine of 2t squared minus 2 sine of t squared. I just distributed it in. So 2t times that and -1 times that. So there's your y derivative, or dy over dt. Okay, so we got to find the acceleration vector at time 4. If these are the component velocities, the x velocity and the y velocity, what do we have to do to those to figure out the acceleration? Think about your order of equations. If you have velocity, what do you have to do to get acceleration? You can say it louder. Yeah. Derivative, okay? So we're going to take the derivative of this x velocity, and we're specifically going to plug in 4. So maybe instead of doing it by hand, we can use our calculator. Same thing for dy. This is the velocity of the y coordinate. We want to take its derivative, and we're going to plug in 4. So we'll get our overall acceleration vector at time 4. Let's see, for the x acceleration, I got -15.322. 0.408. Does that work too? How are we doing with velocity, acceleration, displacement, all in terms of these parametric equations where you have two separate equations, an x and a y? Doing okay? All right. That's basically it for this section. It was just practice with the different terminology and values that we can find. So maybe we'll try some homework problems tomorrow just for practice, and then we'll start the next section on Tuesday, or Wednesday, sorry.